Welcome to the fifth lecture in the series on sequence of functions. You may remember last time we did investigated the relation between uniform convergence of continuous functions and continuity, whether the limit function is continuous, and we also proved if f's are continuous and closed and bounded interval, if they converge to f, then of course f is continuous, hence it's integrable, and integral of fn from a to b converges to integral of f from a to b, right? So today what we will draw some corollary using fundamental theorems of calculus from that, and also we will extend this result something like if f's are integrable and if f's converge to f uniformly on closed and bounded interval ab, the resulting function f is also integrable. Okay, compare this what we proved. We assume f's are continuous and fn converge to f uniformly, therefore f is continuous, and hence it's automatically integrable. You understand? Therefore integral a to b f makes sense. So we only have to prove integral a to b fn, this sequence of real numbers, converge to the real number a to b f. This time what we have to prove is f is integrable, that is integral a to b f also exists, and the sequence of real numbers converge to integral a to b. That's actually repetition of the earlier proof. So the crucial point is to prove f is, the limit function f is integrable. Yeah, so these are the two things. Hopefully about 40 minutes should be enough. Okay, let us start sharing. Yeah, so let us go to the earlier thing. So fn's are sequence of continuous functions a, b to r. Okay, continuous functions, and if fn converges to f uniformly on a, b, then we proved f is continuous. Okay, this is a theorem we proved. Okay, right. Now what I want to do is something else. Suppose I have fn's, this is another, okay, this is over. Now fn's and f, let us say from a, b to r, okay, they are actually C1 functions. What is meant by C1 function? Continuously differentiable. That is f dash exists and it's also continuous on AB. Continuously differential on AB. Right? What I want to know is, suppose fn converges to f uniformly, and remember fn dash are also now continuous functions, right? And suppose it also converges uniformly to some function. Do you follow that? Fn's are uniformly convergent to f, and fn dash converge uniform to some g. You understand this? Okay. And remember fn dash both are continuous, therefore g will also be continuous. Is that clear? Now what is that you would like to say? Think. Develop your intuition. You may be wrong. What we want we may not get, but it's all right. We should dare to guess. Okay, what do you think I should say? Fn's are continuously differentiable, they converge to f, therefore f is continuous. Fn dash are continuous, therefore they converge uniformly to some function g which is also continuous. So what would you like to say? I would like to say that f dash exists and it's equal to g. Is the result clear? So fn converges uniform to f, fn dash converges uniform to g. Then what I want to claim is then f is differentiable. Not only it's differentiable, and its derivative must be g. Since g is going to continuous, so actually I am proving f is continuously differentiable and its derivative is g. Do you understand this? Yeah, the proof is very easy. Okay, this is what we want to prove. Later we will actually prove something. Anyway, let's not worry about it. What happens later, we want to prove that. Yeah. Now how do you prove this? See, for all higher analysis purpose, most often this theorem is very good. Okay, there is a more technical result, I will come to it later, but this is the most important, simplest case, and it's the most useful case. So how do I do that? Now notice that, is there any relation between f1 f1 dash? Yeah, all of you know that, right? It is given by, yes, fundamental theorem of calculus. So that gives us a relation between f1 and f1 dash. What does it say? So fix some point C in AB. If you want to take even interior point, I don't care. Yeah, what does it say? Fn of x is Fn of C plus integral C to x of Fn dash t dt. This is what fundamental theorem of calculus says. X could be here or here, I don't care, wherever. Yeah, you understand that? This is Fn dash, sorry, Fnc, Fnc C to x Fn dash dt. This is fundamental theorem of calculus. Is that all right? Okay, all right. Now I think I'm happy. Now what do I know? I know that Fn dash converges uniformly to G on AB. You understand that? Therefore Fn dash, do you remember we already said that if some Fn converges to F uniformly on a big set, it converges uniformly to F on any subset also. Therefore Fn dash converges to G uniformly on Cx, or it may be Xc. You follow that? Right? Therefore, by the last theorem, which you had already proved, then I know that C to x Fn dash t dt should converge to integral C to x f of t dt. G of t dt, because Fn dash converges to G uniformly. You follow that? Okay. Now where does Fn C converge to? It converges to f of C. Why? Because F1 converges to F uniformly, therefore it also converges pointwise. Therefore at the point C, Fnc converges to Fc. Is it all right? Very good. Now where does Fnx converge to? Again, for the same reason, uniform convergence implies pointwise convergence. Therefore, okay, if I take a limit as n, Fn of x equal to Fn of c, I am taking the limit for the entire thing, plus C to x Fn dash t dt. Where does this converge to? It converges to f of x plus, equal to f of c plus integral C to x G of t dt. Do you agree with that? Yeah, okay. Is that all right? Good. Now let's understand, what does this say? This says, remember, now I can use second fundamental theorem of calculus. If g is a continuous function, right, and if I take integral C to x G of t dt, call it capital G, G of x, then I know g is differentiable and g dash x equal to G of x. Do you understand that? Yeah, right. Now the f of c is a constant also, therefore it's also differentiable. You understand that? Therefore this right side is differentiable by fundamental theorem of calculus. One of the fundamental theorems of calculus says this is differentiable and its derivative is G of x. Therefore this sum of differential function, therefore f is differentiable. And what is f dash of x then? Derivative of this fellow, which is 0, plus derivative of this fellow, which is gx. Therefore f dash x equal to gx. And since g is continuous, f is continuously differentiable. Do you understand the proof? Okay, pause, review and proceed. So what are the results we used? Just reflect upon the proof. We used if f1 is continuous, if f1 continues f uniformly, f is continuous, we used it. And second, if fn's converge uniformly to fn's are continuous, then f is continuous. Therefore integrals of a to b fn makes sense, integral a to b f makes sense, and integral the sequence of numbers integral a to b fn converge to integral a to b f. Okay, we used both these results. Do you understand? Next, we also used fundamental theorems of calculus. Yeah, isn't the proof easy? Yes. Okay, all right, but let's go through the proof. Did I really need the fact f1 converges to f uniformly in this? I needed the fact only f1 converges point-wise, because fnx converges to fx and fnc converges to fc. You understand? Yeah, therefore I can relax this hypothesis. The hypothesis will say f1s are still continuously differentiable function, right? And f1 dash converged uniformly to g, therefore g is continuous function. Now what I am saying is f1 converges to f point-wise. That's good enough. Do you understand the proof? Because I did not use the fact f is good. Do you agree with that? Sure? Yeah, because integral, see, when I wanted to say integral, see, what did you want to use? You wanted to use some such thing, integral limit of sequence of functions, something, let us say hn equal to limit of integral hn, right? Where did we use? That was only when fn dash, but fn dash are already continuously differentiable. Fn dash converges to g uniformly, therefore I can use that. So I did not need the uniform convergence of fn. I needed only point-wise convergence. How many of you appreciate this? See, whenever you go through the proof, this is the kind of thing you have to learn. Go through the proof, understand the proof. Next time, see what are the hypotheses we used. Okay, whether we needed the full hypothesis. See, this is how one learns. One tries to generalize the theorem or tries to understand the theorem. And this kind of investigation and exploration also makes you understand, so that most often you don't remember, because your brain has picked up all the details, so it can reconstruct the proof on its own very quickly. I hope you understand what I'm saying. Yeah, okay. So but I think I can say something more. So with the same hypothesis, let us assume fn's are continuously differentiable, and let us assume f and c converge to point-wise. Call that number as f of c. Okay, it converges point-wise to some number. I am calling that number f of c. I am not saying f is a function now. Please understand what I am saying. If you want, it converges to some lambda. You understand that? Yeah, and f1 dash converges uniformly to g on AB. So what I am assuming now, f1s are continuously differentiable, and at a point c in the interval, f1 c converges. That's it. This is a sequence of numbers, it converges, nothing more. And I have some hypothesis on f1 dash. What is that? The derivatives f1 dash converge uniformly to g. Right? Then I want to know whether the result still is true. Are you following? Okay, usually textbook, if at all they give the proof, they will start with this proof, but that's not the way. People, what they do is they put something, analyze the proof, then slowly improve upon the result. This is the kind of thing which is never taught. Okay, but when you want to go higher mathematics and do research, you should learn how to do this kind of thing. Okay. So I want to know. So what is that I want? So this is hypothesis 1, and this hypothesis, if you want, this hypothesis 1, this hypothesis 2, this hypothesis 3. Do you understand? Then what do I want to know? I want to know whether f1 converges uniformly to some pointing on AB. Okay, and what do I want? F dash equal to g. Do you understand? This is the theorem I want. Let us try to prove. Okay, there will be something which I am out to I do not know. Let us see. Let us try to see. So what do I want? I want to know whether f1. Okay, how do I prove that? See, now f is not given. So how do I do that f1 converges uniformly? This is where the next result comes. Okay, so we will need the concept of Cauchy sequence in the uniform sense. Okay, let us just break it. Let's not worry about it. I will come to it. Okay, when in the next lecture I will come to that. Okay, so let's try to estimate. We will see that. Okay, now let us do what is that I want. fnx minus fmx is what I want to estimate. You understand that? Okay, some kind of convergence. See, I want this to converge point wise. You understand? I want point wise convergence, because in the early result what did I need? fnx converges to f of x, fnc converges to f of c. So I just needed point wise convergence. So let us see whether I can do that. Okay, so to check point wise convergence, that means I want to say fnx is point converges, that is fn point wise converges. Okay, to show this sequence of real numbers converge, what should I do? I have to show fnx is Cauchy. So that's what I want to do. Okay, as you can see, I'm thinking here. Okay, so what is fnx? Again, by fundamental theorem calculus, it is fn of c, okay, plus integral c to x fn dash of t dt minus fm of c minus integral c to x fm dash of t dt. You understand? Now what do you think I will do? I can rewrite this fn of c minus fm of c, right, plus c to x fn dash of t. By linearity of integral, it is fm dash of t, the whole thing to dt. Yeah, so what do I want to show? I want to show this is point-wise convergence. That means I have to show this is Cauchy. Therefore I have to estimate this. Therefore it is this. Yeah, therefore it will be less than or equal to this fellow and plus modulus of this, but then that's less than or equal to this. Are you happy now? Yes, agreed? Okay, so what do you think I have got? Okay, now by hypothesis 2, right, hypothesis 2 says f1c converges, right? Therefore f1c is Cauchy, right? Therefore given epsilon, okay, there is an n, so that for all n m greater than or equal to n, modulus fnc minus fmc will be less than epsilon by 2, because it converges. Therefore in particular it's Cauchy. You understand? Now for this, what will I do? I know again fn dash of t, okay, fn dash converges uniformly to g, right? Therefore fn dash of t minus fm dash of t I want to estimate, but this will be less than or equal to fn dash of t minus g of t plus g of t minus fm of t. Do you understand this? Yeah. Now what do I know? I know fn dash converges to g uniformly, right? Therefore if you give me an epsilon, okay, for epsilon by 4 there is an n, if you call it n1, call it n2, so that for all nm greater than or equal to n2, this fellow will be less than epsilon by 4 and this fellow will also be less than epsilon by 4. Therefore this is less than epsilon by 2. Do you follow that? Therefore the second term is less than epsilon by 2, right? And this and multiplied by distance between c and x, but that also it will be of 2 points in the interval ab. Okay, c and x may be 2 points. Okay, c may be here, x may be there, or other way around. But the modulus x minus c, see, this fellow will be less than epsilon, something to do with epsilon times the length of the interval, but the length of the interval will be at most b minus a. Therefore what can I do? Okay, I can try to be smart. B minus a into b minus a. Yeah, so this, therefore this, the integral c to x fn dash of t minus fm dash of t in modulus will be less than or equal to mod c minus x into epsilon by 4 into b minus a. Okay, this plus this, okay, 2 times, yeah, epsilon into, if you want, okay, this will be 2b minus a, all right, but this will be less than or equal to mod b minus a into epsilon by b minus a. Are you following what I'm writing? This minus this will be less than this plus this, therefore 2 times epsilon by 4b minus a, therefore epsilon by 2b minus a. Yeah, are you following? This is epsilon plus epsilon, therefore it's a epsilon by 2 into b minus a into modulus this by monotonicity of the interval. This is less than epsilon, therefore total length of the interval mod c minus x, but that in turn is less than equal to b minus a. I hope all of you understand. All right, so what do you think I have proved now? I have proved that this integral is also less than epsilon by 2, yeah, and this is less than epsilon by 2. So if I take n to be greater than or equal to maximum of n1 and n2 and okay n and m, okay, then what happens? Mod fn x minus fm x will be less than epsilon. You understood that? And for which x? Notice that for any x in the I proved it. Yeah, keep this in mind. In the next lecture we'll understand what it means. Something happening. Okay, okay, there's a flash. Keep this in mind, we'll come to that, but at present it's not needed. What I have shown that under this assumption, namely fn's are c1 and fn converges at a point, fn c converges for some c in the interval ab, and fn dash converges to g uniformly on ab, then what I have shown now, I have shown that fn converges to some function pointwise, call that function f, right? And that what I am claiming, I am also claiming that f dash equal to g. Have you understood this? Yeah, go back. Why does it follow? Because in the earlier proof I just needed only pointwise convergence of fn and fundamental theorem of calculus. Yeah, please review, pause, review and proceed. Okay, the rest of the proof we saw as earlier. See, please someone do not assume and believe me, trust me. Okay, now that what I have shown now, under that assumption I have only proved one thing: the sequence fn of x, fn converges pointwise to some function f. That's it. Now what I am claiming, in the earlier proof I needed only fn converges to f pointwise and fn's are c1 and fn dash converges to g uniformly to conclude f dash is equal to g. F is differentiable and f dash equal to g. You understand? So I reduce this to earlier case. Under the stated assumptions, fn is pointwise convergence. Okay, please go through this kind of thing. It's fun. Okay, don't get mystified or anything. Math is fun. Now let's look at next technical result. Okay, now suppose fn's are integrable. That is a Riemann integrable on the closed and bound interval ab, and let's assume fn converges to a function f uniformly on the interval ab. What I want to know is f integrable? If it's integrable, then I want to know what's the relation between integral fn a to b dt and integral a to b f dt. You understand the question? So if you write f equal to limit fn Okay, then this one usually what we want to prove is, let's look at the integral of a to b fn dt, the limit of these fellows. This is equal to integral of limit of fn t dt. You understand this? This is the kind of classical way of writing, that is, you are interchanging the limit operation and the integration operation. These two things are interchanging, commuting, right? But what are the assumptions? Fn's are integrable and they converge to f uniformly on the interval ab. Then the limit, taking the limit of the function and taking the limit of the integrals can be interchanged. But modern notation will only say that integral a to b fn dt, this is a sequence of numbers. This sequence of numbers converge to the real number f of t dt. Yeah, but why does this make sense? So I have to first of all prove f is integrable. Yeah, please pause, review and understand the statement first. The proof is easy. Yeah, this is what we proved in the earlier case. There what we would assume was fn's are continuous and fn converges to f uniformly on ab. Therefore I know f is continuous, and hence I also know f is integrable. Therefore integral a to b f of t dt makes sense. So then I proved this result, integral a to b f of n dt converges to integral a to b f of t dt. You understand that? So we are relaxing the condition. Now what is the relaxation? Instead of assuming continuity of fn, we are assuming only integrability. But then there is a twist to the story, right? An extra work for us, namely the limit function f I have to show is integrable. Yeah, okay, let's start with the proof. And once I prove that, the rest of the proofs is exactly similar to the continuity assumption. Okay, by that, no, the rest of the proof is similar to the earlier theorem where we assumed fn's are also continuous. Okay, so the first thing is I want to prove f is integrable. So, right, so what is that I would like to know? How do I prove f is integrable? We know that to prove something is integrable, the easier thing is to use Riemann criterion. That means if you give me an epsilon positive, I have to find a partition p so that u of p minus L of p is less than epsilon. You understand this? Sure. Very good. Okay. Now, how do you think I can prove this? I have to look for a partition, right? You gave me an epsilon, I have to look at a partition. Where do you think I will do? Let's go back to my hypothesis. What did it say? Fn's are integrable and fn's converges to f uniformly. Okay, so this should tell us possibly, okay, if n is very large, choose a partition p, right? If you said that, use Riemann criterion for integrability of fn, I invoke. Are you following what I'm saying? For this given epsilon, okay, for each partition, for n, there is a partition pn, so that u of pn minus L of pn is less than epsilon, because fn's are, so yeah, fn's are integrable. You understand that? So what is my hope? Since fn converges to f uniformly, I expect if n is very very large, right, the same partition pn, okay, fix one such n, okay, fix such an n, then I expect this pn will serve f also. That is, I expect u of p pn minus L of pn will be something or other to do with epsilon. So maybe a constant multiple of epsilon or something. Do you understand this? This is what I should expect. It may or may not work. Yeah, but this is how one kind of explores the situation. You follow that? Yeah, let us do that. Okay, at present let's not worry about, okay, which n, etc, etc. So let epsilon be given, right? Okay, I have to show you this one. I have to find a partition, right? Okay, now for this epsilon, since fn converges to f uniformly, okay, once you give me an epsilon, I can do something to this, right? What do I know? There is a capital N. so that for all n greater than or equal to capital N and for all x, what do I know? Fn of x minus f of x will be less than epsilon. Okay, you understand? So this instead let me call it eta. This eta will be something to do with epsilon. Okay, you follow that? Yeah, this eta will be something like a constant times epsilon or some function of epsilon, something. Let's not worry about. You follow that? Okay, so in particular it's true for this n. Yeah, right. Now let's understand this. So now Fn is integrable. Okay, therefore what do I know? There exists a partition Pn such that what happens? U of Pn minus L of Pn is less than, again something to the epsilon, but let me write epsilon. Okay, how long can I keep writing something? Okay, we will come to that. Yeah, you understand this? So I want to claim some now U of Pn minus L of Pn, okay, is less than something to do with epsilon. Right. Now try to investigate. Okay, don't worry about the proof. You can always read from a book, from my book, or from any book. They all will be the same. Okay, but thinking is more important. Now what is U of P? And let's as usual let us look at partition x0, x2, xn, etc. with the standard notation. L of P will be summation mi of f minus small mi of f into delta xi. What is delta xi? Xi minus 1 is what we call as delta xi, the length of the interval. Okay, right. And what is U of Pn? U Fn Pn minus L of Pn, that is equal to mi of Fn minus mi of Fn, the whole thing into delta xi. Right. So when I want to say this is less than epsilon and this one, what is my idea? Go back. You see that f for h, for every x in the interval, my fn of x and fx will be something to do with epsilon, maybe eta. All right. So what do I want to say? What is that you would like to check? What is mi? Mi of Fn, that is a supremum or LUB of Fn on the interval xi minus 1 to xi. And what is mi of f? That is the same similar object, right? But I know f of x and Fn of x vary only by epsilon interval, right? By epsilon distance. For every x, in particular for every x in the interval xi minus 1 to xi. Are you following? Okay. If you don't, let us look at that. So for any x in the interval xi minus 1 to xi, in fact for any x in the interval ab, okay, what happens? Let's look at fn of x minus f of x modulus is less than epsilon, right? Eta actually I wrote, but okay, you understand? That means where does fx lie? Fx lies in fn of x minus eta and fn of x plus eta, right? Therefore what can you say about LUB of f of x as x varies over xi minus 1 to xi? That will be less than or equal to, you understand that? That is fx is greater than or equal to fn of x minus eta. You understand? Now let me take LUB of both the things as x varies over in the interval xi minus 1 to xi. What will I get here? I will get here mi of f is greater than or equal to mi of fn minus eta. Do you understand that? Yes? Sure? Okay. So can you guess what should be the relation between small mi of f and small mi of fn? You have to do the same thing. Yeah, again look at that. What is small mi? I hope I am doing it correctly. LU, I want LUB, right? Okay, LUB of fx will be greater than or equal to, okay, I think that's fine. Yeah, right, okay. Right, what is the relation between them? Again the same thing. What do I do now? For each x here, let's look at that. Fx should be less than fnx plus eta, right? Therefore, if I take GLB, yeah, then what will happen? I will have small mi of f will be less than or equal to small mi of fn plus eta. Okay, are you sure now? Yeah, please pause, review, proceed if you are in doubt. Okay, now we are through. Let's look at, so my mi of f minus small mi of fn, sorry, small mi of f, what do I know? This will be capital mi of f is less than or equal to, I wanted greater than or equal to or less than or equal to, I wanted something, so let us do that in a minute. Okay, yeah, I think I should I'm sorry, you see that I want to say it's less than or equal to mi of fn minus small mi of fn plus something to theta. You understand? Okay, right, now I'm saying greater than or equal to, so that's not good. So what should I do is, this is less than or equal to fn plus eta. You understand that? Therefore less than or equal to mi of fn plus eta. You follow that? Yes. And similarly, this is greater than, fx is greater than this, therefore mi of f is greater than this, therefore minus mi will be less than. Are you following? Now you see that? Yeah, if you remember the proof, you know what you want, but you don't remember the proof. Or I could actually thought about one step ahead. Usually in the classroom I keep walking, then I will be able to think much better. Since I'm sitting, are you following what I'm saying? Okay, I want to say mi of f is less than or equal to capital Mi. This is the result I want, therefore this is what is going to happen. So this is the one. Okay, and this will be, therefore minus mi of f will be less than or equal to small mi of fn plus eta. Therefore there are two etas. Yeah, therefore if I sum it over I, this object, this will be less than or equal to summing this over I plus, how many times I have to sum it over? Yeah, remember this is going to be into eta times xi. You follow that? Okay, so mi of f minus small mi of f, the whole thing into delta xi. Remember these delta xi are positive. Therefore even for Riemann Stieltjes I can use it. There I will use delta alpha I. Anyway, so summation mi of fn minus small mi of fn into delta xi plus 2 eta times delta xi. Are you following? Because each one of the term will be less than 2 eta. Yeah, but what is this sum? This sum is nothing other than UFP minus LFP is less than or equal to UFN P, my P is Pn, minus LFPN plus 2 eta times B minus A, because delta xi will be sum. Yeah, but I already know this is less than, let us say epsilon by 2. I have to make sure this is less than epsilon by 2. That means I should choose my eta to be B minus epsilon by 4 into B minus A, right? Eta should be less than 2 goes below, therefore epsilon by 4, and b minus a also goes 4, right? That's it. Yeah. So what have we shown now? For p equal to pn, I said that u of p minus l of p is less than epsilon for the given epsilon. That means f is integrable. Yeah. So this implies f is integrable on AB. Once it is integral AB, then integral a to b f of t dt makes sense. Then what is that I have to do? Fn of t dt a to b dt converge to integral a to b f of t dt. That means given epsilon positive, I have to show for n sufficiently large, Fn of t minus f of integral a to b f of t dt in modulus is less than epsilon for all n greater than or equal to some capital N. Yeah, but this proof is exactly similar to the way earlier, but this will be less than or equal to a to b mod Fn of t minus f of t dt. I want this to be less than epsilon, right? So now I can use Fn converge to f uniformly, therefore there exists an n so that mod Fn of t minus f of t will be less than epsilon by b minus a. You understand that? Therefore if n is greater than or equal to capital N, this fellow will be less than epsilon by b minus a, and by monotonicity epsilon by b minus a into the length of the interval will be b minus a, therefore it is less than epsilon. This proof is exactly similar to the earlier proof. Yeah, please go through the proof, pause, review and proceed, and you see that once you have some kind of an idea, you can always work out. Yeah, I hope you all enjoyed. Please go through this proof, and as usual, do not worry about whether you can remember the proof. Just go through, think along with me, and if later if you want, you read any textbook, you will see, oh, this proof is so easy, and you know why the proof is working. And how do I know the teacher knows you have to do something earlier so that the inequality comes properly? Yeah, I hope you enjoyed. Take care. Tomorrow again we will meet with something which I did. Okay, do you remember I put a ping happy face? You will understand what it means tomorrow. Stay tuned. Bye.